Hello and welcome to day 15 of Advent of Code 2024. So this video comes out one day late because I had a lot of other things to do yesterday. So that's why. And also I had a lot of issues with this puzzle when I solved it, and my solutions for part 1 and part 2 are totally different, and I will explain more later on. So let's dive into this puzzle then. So we again get a reference to an earlier year of Advent of Code. So this day is the Lanternfish, which is day 6 of 2021. So they have warehouses with boxes. They have robots in those boxes that pushes those boxes around. And they want you to calculate how the boxes will end up after the robot has made all its moves. So the robot. So this is how the input looks. So we get kind of a map where within this walls we can also find wall elements within our inner area, but the robot will be an @ sign. And all the boxes will be O characters. And the idea is that all these signs here, or symbols, will represent directions that this robot would try to go to. So if we take this, let's say the first, so this robot here will try to go left, then he will push this box one step. Let's scroll down. So the robot will try to move. If we look at this little bit smaller example here, we can see that the robot stands next to a wall, and if the robot tries to go left, well, he can't, so he remains. He remains here. Then the next move is up, so he moves up. Then he moves to the right, and you see that this box gets pushed onto the other one. Then there is a new right move. Then both of these boxes gets pushed in, and there is also another right move. But then the robot cannot push these boxes any longer because they have already hit the wall here. So then it goes down, pushes all those 4 robots down to the bottom. It tries to go down again, but it can't. It goes left, goes down, then it goes right again, pushes that box, and go right again once more, pushes that box into the wall. Then it goes down, pushes that box, and it can't push it any longer because it has this box got stuck onto the wall here. So so these are all examples of how we are going to do here. So in the end here, we want to calculate what's called the goods positioning system, or the GPS for short, which will be 100 times the distance from the top edge of the map plus its distance from the left edge of the map. So basically it will be 100 multiplied by the row plus the column of the box. So after the robot has made all its moves, we want to check all these boxes, check their row and column, multiply it by 100. And that will be our answer. So and they give us that. So for this example here, we need to have 10,092, and for the smaller example here, the sum will be 2028. So let's go into our code here, because I've actually already added some boilerplate stuff just to get the things ready, because finally this code became like 400 lines long. So I will actually try to do this a bit faster. As obviously this is not my original code, so I kind of want to make this a little bit of a learning experience. So I'm actually not going to write every line of code, because that will take too long for me, because I'm not very fast code writer. So I would kind of just cut and paste. So let's begin here. So what we do here is that we begin by reading in the input file, and as we see in it's kind of separated by the double new line. So we get kind of one of our so we get it in two sections. So we get the map in the first section. We split that by its new line. Then we get our list of string as our map, and the moves, they will be the second section of the input. But we need to remove our new line and return characters. Otherwise we can get into problems, because we want all these moves as a single long string without any breaks in it. And also I've kind of created a dictionary here for our movement, which will be like up, we would go -1 0, down we go 1 0, left we will go 0 -1, and right we go 0 1. So that's a little bit how it will look like. So we have our method here that will calculate our part 1 answer. So we begin by defining our rows and our columns. We also want to, the first thing we're going to do is find out where the robot is within our map. So we define our bot row, as we call it, and bot column. We also want to also want to collect up all our boxes positions. So we create a hash set, which will be its row and column, and then we will kind of add these. So if the @ character is found, then we set the row and column to that row and column. And then obviously, if it were several robots, this wouldn't work. But as we know, there is only one robot in this map, so then it will work. And also the boxes, we add them to our boxes hash set. And so then the next thing we do is we're going to go through all our moves. So it's the moves here, yeah. So we can index our dictionary with a move. So we get the direction row and direction column from the dictionary. And we can actually do like this. We don't have to have to type it everywhere. Yeah. So we begin by increasing our robot's position by and we're calling them the new row and new column. So that will be our robot row plus its direction row and robot column plus its direction column. And we begin by checking if the boxes contains this position, because then it means that we need to push that box in the direction. So no, wrong. Yeah. So if the boxes if the box in the path of the robot, we need to have somewhere to we need to check if that box and actually its entire box chain will be able to move it. So we create a method for that, which is called can move box chain. So yeah, we will just add this. So this also requires our kind of sanity check method, that we are still within the bounds of the grid and all those things. So what we do here in this method, we will kind of as long as there are boxes within our row and column here, we will increase the row. So we know that there is one for the first, for those we send in, but we will continue increasing the row and column in the direction. Check if that is a valid move. If it's not, we will return false. Then if we return false, we cannot move that box chain, because somewhere down the line in those robots we turn into a wall, probably. But if all goes well, we will return true. So we have kind of our first condition check here, that we can move our box chain, and the move. So if we can move our box chain, we will kind of have also another method for that, which will obviously be called move box chain. So we will move our box chain, and then so move box chain kind of works a bit like the same. So we try to collect all our boxes that has this row. So we add them to kind of a list here, a list of its positions. We add them to the list. Then we will increase the row and column, and we will do this until we exhausted all the boxes within this line. Then what we do, we reverse those boxes' position. Then we kind of remove them in that order, and add and just. So what we do basically is that, well I can actually show you here in our drawing. So let's say that we have our robot here. So we have our robot here, and and the robot is going in this direction. We have kind of boxes here, and as let's say we have 4 boxes here, then we have kind of dots afterward. What we want to do here, we want to move, and the move here it's going in this direction. So we want to imagine that this robot stands next to all these robots here. What the next state of these robots should be like this. And then the robot will be here. So what we do by reversing the direction of those robots, we will kind of, and then removing them in that order, then adding them plus the direction, we will create this structure. So that's basically how we do it. Okay, so let's get back to the code then. So that's the moving part. Then we update the robot's position afterwards with that new row and new column. So now it's kind of, now we have moved all those boxes, and then we're kind of set. And if not the box is in the robot's path, we will just move that robot, but we also need to check that that robot can be moved. So then we use our little isValidMove method again, and then we set a new row and new column to our bot row. So that's basically what we do. And yeah, we can actually because I think we have set up. Yeah, we're gonna do the test input. Yeah, so we're going to do the test input here, and we have our but we have one thing left to do here actually, and that is calculate this GPS sum. So let's do our boxes. Let's do our boxes. So we can sum. We can use this. So we can say B. So we will take 100, multiply by B row plus B column. So that will be our GPS sum, and we will kind of return it. So I'm thinking just to draw a map here. So we will kind of yeah. No, we need to have also the boxes. Yeah, this is just my little helper method here to just visualize the map. So let's draw it after we have made all our moves, and then we can see the result here. So let's run it and see how it looks. Yeah, so we can, if I just bring up this again, we can see now that it looks completely right here, and also the value here is what it should be. That's that 10,092 value here. So that is our solution for part 1. It's actually, yeah, so I'm just gonna turn this off, so then we can jump right into part 2 here. Yeah, so the thing is that I'm pretty satisfied with this solution that I did for part 1. I obviously try to use that for my part 2, but But it was not possible, or well, it should have been possible. But I actually went down a real rabbit hole of coding, and for some reason I couldn't get my part 1 solution to work with those modifications, and I struggled with it. Spent like 2 hours fiddling with that. Then I just gave up, so to speak, and began with a new clean slate, so to speak. I just tried coding it from the ground up instead. So the way I did it was like instead of the solution I have for part 1, where I store the boxes in the boxes positions is stored in a hash set, and I kind of don't actually physically move them in the grid, so to speak, but I kind of move them just within that hash set. And the robot will be basically the same, of course, because that's just indicated by its row and column. But what I did was more or less, instead of moving those and having those things in a hash set and moving them kind of in memory, my solution for part 2 actually, which is the way it worked, was to do the actual moving within the actual map grid, to do it in place, so to speak. So okay, let's so that's a bit of my explanation. So I will try to guide you through how my thinking was, but yeah. So the part 2 of this problem is that there is a second warehouse, but that warehouse is well, it's similar to the one you just helped them with, but and its list of robot movements won't change, but the layout and the things are different with this. So what I want you to do is kind of make it wider with. So like if there's a hash mark, there will be 2 hash marks. If it's a robot, the robot will now contain 2 characters instead of 1. When there's a dot, there's 2 dots, and when there is the robot, it will be the robot plus a dot. So this will kind of produce our warehouse map, which is twice the wide and twice as wide, and will have the boxes will be like those characters. So the way this can work now is that, for instance, boxes can now move other boxes, but not just the boxes right in front of them. They can also move boxes, like in this example here. The robot kind of pushes on this side of the robot or the box, but that means that this is kind of a total. But that means that this side of that box will touch this side of that box, and this side will touch this side of that box. So that will push them all up, and as long as some of these boxes within this kind of, I mean, you can imagine there is more boxes up here, but as long as one of those boxes will turn into an obstacle, you cannot move them anymore. So this is a significantly more complex problem than the first problem, of course. But it's still the same for the GPS for the GPS calculation. So you still calculate it by 100 multiplied by the the row and column. So that is actually the row and column from the left edge of the box. So it's kind of that. If we will just calculate the position of this character. Yeah. So let's go to our code, and kind of for this example, the GPS characters will produce this answer. So let's go into the code and check how that went. So we can actually collapse all these methods because we will not use any of them for our part 2. We can just push them down a bit. What we can do actually, we can actually remove all of them. That would probably be easier. We can let them be. Yeah, so our part 2 will kind of I will just try to do it like this, like I did for the other one. So we will have our we'll have a method that does this calculation as well, and this will calculate our part 2. So we kind of want to call that method as well. Yeah. So we kind of start with the same kind of basic things. We're going to return the same thing. Obviously we will begin with creating that bigger warehouse. So we have this method for that, and then we will I will basically just do this in kind of blocks here. Yeah, so with this, creating this larger warehouse, I did a method that takes in this kind of list of string map. The reason why I needed to convert it kind of to a char array of arrays is because now we're gonna modify elements in those, and it's not possible to do it in, well, it's possible, but it's much harder to work with like a list of strings. So that's why I did it. So I create kind of a scaled map, scaled row, and yeah, basically what is said. If I turn up, if the current column is a pound sign, we will kind of add 2 pound signs. If it's a box sign, we will add those new box characters. If it's a dot, we will add 2 dots, and if it's a robot, we will add a robot plus a dot. So that basically creates our kind of grid. Then we want to find the robots row. That's kind of the same as before, because now we have the bot row and bot column. Yeah, but now we don't collect any boxes because we only want to find the robot. And then we will do the for each of our moves, and yeah. And now we kind of separated out our direction row and direction column. So as I just coded this up in a different class file when I created it, I kind of didn't actually pull. I didn't pull much from the part 1 code that I succeeded with. So it ended up like this. So we have our kind of direction row. So if it's up, we will go -1. If it's down, we will go +1, and left and right will be -1 and 1. And then we will have our move targets list, which will be our we will initialize it with our robot, because we are going to move our robots. But the move targets will if we find boxes in the robot's path, we will also collect them in that move targets list. And we have kind of a boolean that we can set that if it can move, then we will do a for each loop. So this will be like the way not for each. We will do a for loop, and that's why, because within this for loop we're going to add items to that move targets list, and we cannot do that in a for each. So we begin by checking in our we begin by taking out our current row and current column from our move targets, which initially we will, and for every move the first one will always be the robot. Then we kind of move. We kind of looks ahead in the direction that we're going, which will be with our next row and next column. We check if that's already something that is within the move targets list, because then we will just go to the next, because we don't want to process things twice. Then we look at what is the character at the row we're looking at, and if the the first condition we are going to check is if the current char is a wall, then we cannot move and we will break. If it is the left edge of a box, we will add that position to the move targets, but we will also add the right edge, and that will be the next column +1. And the other way around is if we find the right edge of the box, then we will also pick up the left edge of the box. So that will be our kind of loop where we collect up the boxes that we want to move. Then after this we want to check. So if we have turned into a wall and we cannot move, then we will kind of just move on to the next. And because we're actually going to do modifications to the grid itself, we begin by actually creating a copy of the grid before we start modifying it, because otherwise we don't have track of what's in. I mean, that way we can preserve it while modifying it, so to speak. So so we will begin by taking our grid, our bot row, and our bot call. So we will begin by setting the position where our robot is to a dot. Then we will kind of move our robot. So we will take the robot's row position plus our direction row, and we will take our robot's column plus our direction column, and that will be our new location for our robot. So this is partly the reason why we do a copy of the grid, because otherwise we want to we will kind of write over our box, possibly if we have boxes in our path. But yeah, that's the reason, and so we will also actually, because our first item in our move targets list will always be our robot. We will take all the move targets, and that's the BRBC is representing the box row and box column. But we skip the first because that's the robot. We will just clear the path, and then we will. That's more or less like a housekeeping thing. And then we will do the same. We'll loop through the move targets, skip the first, and then we will kind of do the shifting of those boxes. So we will take the box row plus direction row, box column plus direction column, which will be equal to its old location within the grid. But that's also part of the reason why we do a grid copy, of course, because we want to take what was before and transfer it to its new position. And at last we do our take our bot row and update it with our direction row, and do the same for our bot column. Yeah, so that's a kind of shifting. Then we will shift our robot's location, and then we will kind of take the next move, and we will go through all these moves that will move these boxes. And then when we're done, we need to calculate the GPS sum. So that will be kind of within here. So we kind of loop through the grid, check for everywhere we find this character, which will always be our left edge of the box. We will increase our GPS sum with this calculation, and in the end we will have our GPS sum. So if all goes well, we will have our part 2 answer now. Yeah, so 9021 is the part 2 answer for this example. So that's basically what I wanted to show you, and yeah, I mean, of course, I'm not completely satisfied with the solution. I usually tend to want to do these solutions in the same sense. So that's I tried to use the part 1 solution for my part 2, but So this will probably be something I'm going to return to after this years of advent of code and rewrite, because I don't want to have this on my GitHub. So that's the reason. So yeah. So let's say goodbye now, and I will be doing another video for day 16 right after this. Thank you. Bye bye.